All right, let's get started. Sign-in sheet. I don't have a whole lot in the way of major announcements. I should have mentioned this in concrete. Now, it sort of slipped my mind because I was trying to get into the lecture and whatnot. I sent everybody in civil an email this morning about the DOH. They have a recruiting session tonight at 5 p.m. over in 1203, I think it was. It was on the email. But it's at 5 o'clock. They're looking for interns. They're looking for career positions when y'all graduate. And they're bringing food. Do I need to say any more? I know that when I was in undergrad, free was like one of the 5 food groups. So yeah. But in all seriousness, I mean, it's a pretty good opportunity. And the thing about the DOH is it's not really, nothing in this world guaranteed, but they have a really strong potential path towards licensure. So it's definitely something to consider. You'll have a homework due on Friday. You're well within your ability to do it. And after today, I think what we'll do today is all of the stuff that we've been talking about with net area and shear lag factors and all this, it'll sort of all come together. And if there's a big picture to be obtained, it's today. So what we're going to do is a full-blown analysis example, start to finish. And with that analysis example, we'll be able to get into the prospects of design. So with that, I just want to get right into it. Now, let's see. Let's go back to this. Okay, so I think this is a good place to leave off, or to start. So we've been talking about attention members for the last few lectures, and really, actually, that's not really accurate. We haven't really been talking about tension members, but we've been talking about these ancillary issues related to tension members. So let's talk about tension members specifically. We have so far 2 what I would call strength limit states that we are assessing to identify the strength of a given tension member. What is our maximum capacity before we say that the member will experience failure that's detrimental to safety? Okay. One of those is gross section yielding. So FYAG is the nominal capacity, and then the resistance factor is 0.9. For net section fracture, the nominal capacity is FU times the net area times U, the shear lag factor, and then our resistance factor is 0.75. And so you could theoretically stop the discussion right there if you had a clear understanding of net area and of shear lag, which is why we spent the last few lectures covering that, because that's sort of a really critical aspect. So we talked about the net area for bolted connections. I think we, hammered that into the ground, or I guess drilled that into the ground because of steel. I don't know. Bolted into the ground. I don't know. The net area equals the gross area minus the area lost due to the presence of bolt holes plus any necessary stagger factors. And remember, the hole diameter is taken to be the bolt diameter plus 1/8 of an inch. Again, that is the case now for tension members. When we get into connection land, that's going to change. Forgive me for that later, because we're going to be looking at the physical connection, so we're actually going to look at the physical hole. We're going to use a 1/16 of an inch later, but that's later. For now, we use 1/8 of an inch. Then our shear lag factors, they come from Table D 3.1. U2 is arguably the most common one. 1 minus the connection eccentricity divided by the connection length. Now, our slenderness limit is not a strength limit state, more as it is a service limit state. And it states that the slenderness being the length divided by the radius and gyration, must be less than or equal to 300. Now, without getting too far down the rabbit hole, one of the things I'll say is that right now, slenderness is little more than just like a check that we're going to do just to make sure that the member isn't too flimsy during shipping and during member erection and things like that. When we start getting into column land and we start getting into beam land, L over R is going to be very important. It's going to be a very, very important quantity, because how slender a member is directly proportional to its capacity under buckling. And columns and beams, that is the story, is buckling. So L over R is going to become very important later. For now, it's just a check, but later on it will become important. Okay. Now, Right now, I've just got gross section yielding, net section fracture, and some fundamental equations. We're going to add to this equation list later when we start looking at design expressions, when we look at block shear, and we start looking at threaded rod design. But for now, this is enough to get started. So speaking of getting started, I want to do a full-blown analysis example of a tension member start to finish. So I have a W8 by 24. It's being loaded in tension. I have 2 lines of bolts through each flange. Each line has 4 bolts. Remember, lines run parallel to the stress. I have 1, 2, 3, 4 lines of bolts in each flange, 2 lines per flange. The member is 40 foot long. It is comprised of A992 steel, and I'm using 3/4 inch diameter bolts. So I want to determine the design axial capacity of this tension member, and I want to determine if the member meets slenderness limits. Okay? So I'm going to give you all a sec to jot some stuff down, and we're going to get right into it. Hopefully you brought your AISC 15th edition steel construction manual. I think everybody has. That's what I like to see. Oh. Okay, all right. I was about to call on you. That's what I like to see. All right. Everybody have this? Don't worry, we're going to jot down a great deal of stuff with this. Do I need to keep this up here a little bit longer? Everybody good? All right. Again, if you need more time, don't hesitate. Tell me to, Dr. Mike, go back. Are you kidding me? Okay, example 4. All right. In order to do this problem, we're going to need some section properties for a W8 by 24. Okay? Now, we're going to need a lot of them, and some of them you're going to think, why do we need all these properties right now? Don't worry, they'll become clear. So, we need to look up the properties for a W8 by 24, so I want everybody to open up table 1-1. I want everybody to find that W8 by 24, because we need some properties for this. So this is in table 1-1. Now, I'm going to start you out. I want somebody to tell me what the gross area is of a W8 by 24.
7.08.
7.08 square inches. Everybody okay with that? Now, we're not done. We're going to need a lot more than that. I'm curious, can anybody look at the problem? So here, let me do this. Here's the problem. Can anybody just look at this problem and tell me what's one other quantity we're going to need? The extra, well, we'll need that later. I'm going to hold off on that for now because the particular quantity that we use is not going to come from this. It's going to come from the WT. But I'm thinking about net area. What are we going to need?
Flange thickness. The
flange thickness, because the bolts are going through the flange, so I need the thickness of the flange. Okay. Now, what is the thickness of the flange?
0.4.
0.4. Everybody else able to find that? Okay. Now, this is not going to make sense right now. It will later. I'm just saving you a little bit of time. We're going to need 2 quantities. We're going to need the width of the flange, and we're going to need the depth. You'll understand why we need it later. I'm saving you some time now. Somebody tell me the width of the flange. Somebody else.
6.5.
6.5 for B sub F. What about D? D for W8 by 24.
That?
Yes.
7.93.
Yes. Again, it doesn't stick, like, why do you need those values now? It'll make sense. One other thing I'm going to have you all look up is I want you to tell me what Rx is and Ry is. So, somebody else. What's Rx and Ry? What's Rx?
Me?
Yep.
Alright, it's 3.42.
3.42, and somebody else give me Ry.
1.61.
3.42, 1.61. Now, the reason I had you look up both is because I just wanted to use this as an example, but for W shapes, Ry is always smaller for every one of them, okay? It's a shortcut for problems like in tension members. All you have to do is look up Ry for a W shape. For angles and other things, you know, we'll discuss that later, but there we go. So far, so good? Now, if I'm going to compute capacities, remember, for instance, what's gross section yielding? 0.9 Fy Ag. Now, Ag, I've already got that, it's 7.08. But in order to compute capacities, I need material quantities. In other words, I need to look up some properties for A992 steel. Remember, the problem stated that this wide flange is comprised of A992 steel. So I want to see if anybody remembers where to get the properties for A992 steel. See, you're at the right table. You're at the right table. You are not at the right table. Now, if you remember, I had this in my slides as something that you should tag. All right. You're going to see the table and you're going to go, oh, yeah. So what we're going to do is we're going to go to table 2-4 on page 2-48. Y'all remember that? If you have not yet tabbed that table, I would do so, because you're going to be using that table for the rest of the semester. So, now, if I have A992 steel, what can you tell me about A992 steel?
The Fy value?
And what is the Fy value for A992 steel?
50 KSI.
That is correct. What else can you tell me about A992 steel?
The Fu.
The Fu. And what is the Fu value for A992 steel?
65 KSI.
65 KSI. Now, a couple other things that's worth pointing out. You notice that the little grid of gray and black squares and all that stuff. Okay, does anybody notice something about the A992 steel? Are there any black squares next to that? And what is the black square corresponding to up top?
W.
A W shape. What that means is this: if I go to Huntington Steel right now and I go buy a W8 by 24, chances are it's going to be grade A992 steel. Those black squares are corresponding to the preferred material specification for a given rolled shape. So angles like L shapes are most likely going to be of grade A36 steel, and HSS has its own grades, and so on and so forth. Does that make sense? HPs have their own grades, and so on and so forth. So when in doubt, if you're in design land, those are going to be the preferred material specification, so use those, unless I tell you otherwise. Sound good? So, is there anything stopping us from computing the gross section yielding capacity right now? I mean, what's the gross section yielding capacity? 0.9 times Fy times Ag. We have everything. Let's just do that now. So, gross section yielding. So VPN is 0.9 FYAG. So 0.9 times 50 KSI times 7.08 square inches. And so what does that come out to be?
$318.6.
318.6 what?
KSI.
Nope.
Okay.
Kips.
Yeah.
Because it's KSI times inches squared. Okay. And so I'm going to underline that because that is an answer. It may not be the answer, but is at least an answer. Okay? So if I yank on this, my usable strength under that limit state is 318.6 kips. I would then take that and compare it against some factored loads to see whether or not I have adequate capacity. So we'll address that here in a second. Okay? So that is my capacity. That's my VPN under gross section yielding. What about my VPN for net section fracture? What's the expression? It's 0.75 times FU times the net area times U, right? So I obviously have the 0.75, I've got FU, I need this and this, right? So let's take them one at a time. Let's look at net area. So net area, so the net area equals the gross area minus the area lost due to the presence of bolts, plus any necessary stagger factors. So I want somebody to help me out. Looking at this connection, are there any stagger factors that we're going to need to consider? No, there's nothing diagonal, right? There's no diagonal failure path. It's a pretty grid-like pattern. So we can pretty much negate any necessary stagger factors. So all we have is the gross area minus the area lost due to the presence of bolts. Okay? So, help me out. What was our bolt diameter for this problem? If I remember?
3/4 inch.
So if it's a 3/4 inch diameter bolt, what's the whole diameter? 7/8? All right. Now, what are they going through? What part of the section are they going through? Are they going through the web? No, they're going through the flange. So the area of a single bolt hole is going to be the diameter of that hole times the thickness of the flange. Hence why we looked up the flange thickness and not the web thickness. Now, the $64,000 question is, the gross area minus the area lost due to the presence of bolt holes, how many bolt holes? The thick cross-section. Samurai, sword, or lightsaber. 4. Because if here's my eye section, here's my eye shape. God, that's horrible. That's a little better. That's a little better. That's my eye shape, right? In 3 dimensions. So I've got 1, 2, 3, whatnot. So if I'm cutting through this, I'm cutting through 1, 2, 3, 4, right? So it's about perpendicular cuts normal to the axis, okay? So it's not, you don't just count up all the holes in the section. It's the holes along that given cross section, okay? That make sense? So don't forget that part, okay? So it's the gross area minus the area lost due to the presence of bolts. And so that's going to be 4 times the hole diameter times the flange thickness. And I'm feeling a little lazy, so I'm just going to do all this all at once. So it's the gross area, 7.08 square inches minus 4. Now for my hole diameter, what do I put there? What would we say, 7/8? And I'm doing that because it's 3/4 of an inch plus 1/8 of an inch times the flange thickness, and the flange thickness is 0.4 inches. Now, if I'm going too fast, or if this is like, you need a set to take all this in, again, if you have any questions, please, this is what we're here for. So we'll say 2 decimal places, keep it simple.
5.6.
5.68, do I have a second on that? All right, so that's our net area. Again, obviously less than the gross area. So far, so good? So, what do we have? 0.75 FU, net area, we have this, right? So, where do we determine our shear lag factors? Anybody remember the table?
D 3.1.
D3.1, right? So that means we got to turn to table D3.1. I'm going to go on to the next panel. Actually, you know what? I'll write this down. So shear lag factors. How many of you have yet to place tabs in your manual? Starting to look valuable, right? I told you. D3.1, and that's page 16.1-30, is it? 30. So we're going to wait until everybody gets there. One other thing I will go ahead and tell you, for this example, we pretty much go through all of the tabs that you need right now. Because we go through the yield stress, the material properties, FY and FU. We go through the rolled shapes. We're actually getting ready to turn to another one here in a second. And we go to table D3.1. Right now, that's about what you need. We're going to add to it later. But again, if you have not yet started to tab that, I definitely would do so. Okay? Now, help me out. Does case 1 apply to this problem? No. This guy's shaking his head no. Why are you shaking your head no?
The bolts don't go through everything.
They don't go through everything. What don't they go through? The web. That's exactly correct. In this problem, I don't have it on the screen, but I can scroll up. But the bolts for this problem are not going through the web. They're going through the flanges, but they're not going through the web. If they were going through the web, we could simply take U equals 1 and move on. But that's not the most common connection scenarios to have bolts going through everything, unless you're trying to splice members together, in which case it's very common. In this instance, we would not take U to be 1 because they're not going through the web. So if case 1 does not apply, does case 2 apply? Somebody tell me.
Maybe.
Yes, case 2 definitely applies. Because case 2 is when some of the elements go through. Okay, so case 1 does not apply. Case 2, what about cases 3, 4, 5, or 6? Any of those apply? No, they don't apply, right? Because you got HSSs and tubes and pipes and welds and all sorts of stuff that has nothing to do with this problem, right? What about case 8? That's a pretty easy one too, right? It's We're not dealing with angles, we're dealing with rolled shapes or rolled Y flange. But what about case 7? What does case 7 say in this first column? It says WMS or HP shapes where T's cut out of these shapes. We're on to something there, right? Now, with flange connected with 3 or more fasteners per line in the direction of loading. That applies to us, doesn't it? So, would it be fair to say that for this problem we have case 2 and case 7? I think that's a fair assessment. So we're going to have to check both of them. All right? Now, in order to do that, I'm going to go on to the next panel, but I'm going to copy this image over because I want to have this image on the next sheet. Do I need to go back? Anybody need to have anything on this last page? So, continue. All right, so we have case 2 that we're going to evaluate, and then we're going to do case 7. So we're going to do each one separately. Let's start off with case 2. Now, our expression is that U is 1 minus X bar over L. And I'm calling it U sub 2 because it's case 2. All right. Now, let's deal with the connection length first. How long is the connection? Somebody. 11 inches. No.
9 inches.
9 inches. This is, and I did this on purpose. It's really easy for problems like this. I even catch myself doing this when I'm developing homework solutions. Whenever you're determining the connection length, it's from exterior bolt to exterior bolt, from center to center. This 2 inches doesn't matter in that computation. How far is it from the bolt on the outside to the bolt on the outside? It's not 11 inches, it's the 9 inches. Okay? I even make that mistake from time to time myself. So that's easy to make. So the length of the connection is 9 inches. Okay. Now, that's the length of the connection. What about the eccentricity? Okay. So if you remember, the definition of the connection eccentricity is from the connection or the connected face to the centroid. Now, when you have a wide flange that is connected via the flanges, it's a special case. This one's a unique snowflake. Okay. So what we do is we look up the Y-bar for the equivalent WT, okay? Now, what's the equivalent WT? So we have a Y-bar for a WT that is half as deep, so 4 by, and if it's half as deep, it's going to be half as heavy, so it's 4 by 12. And again, imagine that we're just cutting that right in half and looking, let's say, on the top portion. The top portion, that's a WT, it's only 4 inches deep, and it's 12 pounds per foot because it's half as heavy. So now we're going to go back up to the front of the manual to the WTs. So this is, I believe, table, I think it's like 1-8. We're going to find the WT 4x12, which again, I don't think I mentioned this, but that WT table, there's one WT for every W shape. That's in fact how it's generated. So it literally is 1 to 1. So we're going to look up the WT 4x12 and ask what is Y-bar for that, because Y-bar is from the connected face to the centroid. And that's going to be what?
0.695.
0.695. Do I have a second on that value?
Yeah.
Okay, and so that is from table 1-8. And one of the things I try and do on a lot of these problems is if I ever write over here green, like some brackets, and like, that's a reference to where we found that value in the manual, okay? So I really try to make sure that it's not, oh, I just came up with that number. No, we found it in a specific location. So therefore, if we have X bar and we have L, U2 is going to be 1 minus 0.695 over 9. And so what does that come out to be? We'll say like 3 decimal places.
9 or 0.923.
0.923. So far so good? All right. You could probably go to like 2 decimal places, but again, I always like to just make sure that the numbers that we use in class, that if I say 0.923, everybody knows what I'm talking about. So 2 is probably fine, but let's go with 3. So far so good? That's case 2. Now we got to do our second case, which is case 7. Now I want everybody to open that, go back to the shear lag table in your manual, because you'll see what we're going to do here in a second. Now, so if there's any evidence that you need that tabs are necessary, what you're doing right now is evidence of that. Because this is just the nature of steel design. You are going to be flipping back and forth and back and forth and back and forth, especially during celebration time, okay? And so having those tabs is critical, because imagine, like, watch this, see? Boom, I'm here, whereas if you're just flipping through it, imagine how much time you save on the exam. So it's really critical. Okay, now I'm on table D3.1 and I'm looking at case 7. Now, case 7 automatically applies to us since we're looking at a wide flange, and then there are 2 rows that it sort of branches off. The lower one says with the web connected with 4 or more fasteners. We don't have a web connection, so we can just eliminate that, right? We have a flange connection because it's connected via the flanges. Now, do we have 3 or more fasteners per direction in the line of loading? I'm asking you. Do we? How many fasteners do we have per line? 4. In the direction of loading. Remember, a line of bolts is in the direction of loading. So 1, 2, 3, 4, because we're loading it like that. So we have 4 fasteners per line. So that definitely applies. And in order to do this, we're going to compare 2 values, a B sub F and a D. Remember I said that it's not going to make any sense why we look those values up now? That's why we're looking them up. So for case 7, we need to compare B sub F, what was B sub F?
6.5.
6.5 inches, and we need to compare 2/3 of the depth, which is 2/3 of, wasn't it like 7.9 something?
7.93.
And what does that come out to be? 5.29, something like that?
Yeah.
Is that good? Second on that? Okay. So we have B sub F, and we have 2/3 of the depth, and which one's bigger? The B sub F, right? So if B sub F is bigger than 2/3 depth, what is the U value?
0.9.
So U7 is 0.9. Now, here's the kicker. Which of these values do we use? I would read case 7 to give you a hint on that. Use the bigger one. Now that, I'll be honest, that actually doesn't follow, I guess, conservative principles, you would think, because if you've got these 2 values are going to affect your capacity, so the conservative engineer would probably use the lower of those 2 values. However, keep in mind that these are empirical relationships, these are empirical formulas trying to predict a phenomenon that's really complicated. There's remember what shear lag is. Remember, it's that non-uniform stress distribution around the connection, where the stresses get all funky when you've got bolts and discontinuities. As a result, when it says that, it's saying that because this reflects the most accurate answer. Okay, so I know that might seem a little weird, but we're going to go with the larger answer as a result. So therefore, we're going to take U to be U2, 0.923. Now, in an instance where there is no guidance on whether or not to take the larger answer or the smaller answer, I would take the smaller. But when there is guidance, just follow the guidance. Because again, this is trying to hug and fit the test data as close as possible. And again, the data gets real funky real quick. Yes, sir?
So if this was a test question, and you went, like the problem was to do all of this, and you went down and you just stopped at the first U, and that wound up being the one that you used, would you pick up points if they didn't go through the rest of it?
Let me explain my answer. I want you to read case 2, okay? Case 2 says, alternatively, case 7 is permitted for WSM and HP ships, right? Okay, so let's say I get to this point right here, and I look at case 2 and case 7. What does case 2 and case 7 tell me? Well, case 7 says it's either going to be 0.85 or 0.89. And regardless of which one it is, that's bigger, so I'm just going to use that. Right? I have no problem with that as long as you note it. Right? But if I don't know that you considered that, then I don't know that you considered that. Do you see what I mean? In this instance, now that you understand case 7, you could probably look back and go, well, God, we wasted our time computing case 7. Because whether it was 0.85 or 0.9, we were going to use the bigger value anyways, and that's bigger than both of them. So I'm fine with that as long as you make that note. There are going to be instances in here where it's not going to make sense to go through and do the full math. There's a common example in column design, where the way column design works is you pick a sort of a suite of options, like a family of given choices, and you pick the one that's the most economical. And when you're going through the math, you'll see, well, there's no point in checking this one because it doesn't matter what the answer is. This one's obviously going to be more economical. And I have no problem with you not checking it as long as you document it. So, but that'll become clear later when we get to like week 10, week 11, something like that. So far, so good? Okay, so 0.75, FU, net area, and U. We've got everything. So therefore, net section fracture. So we have BPN is 0.75, FUANU, so 0.75, 65 KSI. What was net area? I forget. 5.68. And what's our U value? 0.923. So BPN is what? 255.6. Do I have a second on that value? And then what are the units? Kips. So just to make sure that we're on the same page, so one of the things I always like to do with steel design problems, especially tension members, because there's oodles of different limit states that can affect the capacity, so I always like to put a design summary or an analysis summary at the end. So remember, right now we have two limit states that we are assessing. One of them is gross section yielding and one is net section fracture. When we did gross section yielding, we got a capacity of what? What was it, 3 something?
318.6.
318.6. And we have a net section fracture event of, what was it? 255.6 kips. So just so we're clear, and I know I'm skipping back a bit, but I want to go back a few slides to this right here. So remember, we were looking at a tension member. This is actually very similar to the problem that we're doing because we have a W section, we have bolts through the flanges. And we were looking at all of the different ways that it could fail. One of the ways that it could fail is it just yields out in the main body, okay? And for our problem, that's going to yield at a load of 318.6 kips. The second is that the member fractures right here. It actually separates along the net section, that it cuts in half. And that's going to be at 255.6 kips, okay? Later on, we'll look at this weird one, this block shear one. We'll talk about that later. But again, just to make sure everybody's on the same page, these are just the loads at which those events are going to occur. Now, if I asked you, I said, look, just tell me how strong the member is, okay? How strong is this member? Is it 255.6 or is it 318.6? 255. See, here's the best way of thinking about it. If I have this member and I'm yanking on it, what's going to happen first? I'm going to reach this load before I reach this one. I'm not going to be able to yield the gross section because I'll have snapped the thing in half at the net section first. So how strong is this member? That's your answer. That's the answer right there. So far, so good? Now, I just want to connect this to an idea. Oh, we're doing great. Let's connect this to an idea that you're probably all familiar with, either from concrete design or even just in here. Let's look at our little thought bubble. Let's say the member is subjected to the following service loads. And service loads are just like unfactored loads. So let's say there's a dead load on this thing that, I don't know, let's say it's 80 kips. And let's say there's a live load on it that's 90 kips. Okay? So what would you do if you had a dead load and a live load? You might take those and factor them, right? And so a common load combination that we would deal with is an ultimate load of 1.2 times the dead plus 1.6 times the live. And I'm just curious, if you took 1.2 times the dead plus 1.6 times the live, what would you get?
240.
240. Do I have a second on that? So, let me ask you this. Is this member safe enough to resist a dead load of 80 kips and a live load of 90 kips? I'm asking you. Is it safe enough?
Yep.
Yes, because that is a factored load, again, accounting for uncertainties, of 240 kips, and it has a usable capacity of 255.6 kips. So it is certainly strong enough. But what if this was 190 instead of 90? Would it be good enough? I mean, just looking at the numbers, that ain't going to work. So what would that mean to the designer? What would you need to do?
Use bigger steel.
Use a bigger member, right? And so that's design. That's what design's all about. Sizing that member such that we're safely resisting that load. That is steel design, period. Okay? In a nutshell. So far, so good? Yes, sir.
Is there ever going to be an instance where the gross section yielding is smaller than the net section?
Yeah, that's possible. It's unlikely, but possible. if you've got a really thick member and small bolts, that can happen. So keep in mind, there are other limit states that can govern as well. Like block shear rupture could govern, and we haven't talked about that yet. There's also the idea that maybe the tension member's fine and it's the bolts that fail, or the bearing on the plate can fail. So there's other stuff. So, but yes, it's possible. Yes?
It's a kind of far back, but where did we get the RX and the RY numbers from?
They came from table 1-1. If you go to the Y flanges and go to the page on the right, over here.
On their survey?
And so there's one that says axis XX and one that says axis YY, and it's just the R values under those columns.
Oh,
In fact, I'm getting ready to use that here in a second. So, everybody good? All right. In fact, let me just do that part super quick. So, that's the one thing that's remaining on this problem is the slenderness check. So, does anybody remember how long this member was? 40 foot. That's 40 feet, okay? Now, what we're going to do is divide L over R. R being our minimum radius of gyration. And if you recall, that was RY, which was 1.61 inches. But does anybody see a problem here? I have a member length in feet and an R in inches, okay? So length needs to be converted to 480 inches. Don't forget to do that. When you're doing L over R is unitless, okay? So for it to be unitless, L over R has to have, consistent units. The L has to be in inches and the R has to be in inches. So therefore, L over R is 480 inches over 1.61 inches, which is what?
$298.14.
298.14. Do I have a second on that?
Yeah.
So we'll say 298.1. Is that okay? Why?
It's only 300.
That's less than 300. So one of the things that we do a lot of times in structural calculations is we just say, okay. Whereas if it's not okay, I'll put NG for no good. Okay. Now, what this means is that this member is 40 foot long. If this member were any longer, I'd probably have to make the section larger just because it gets too flimsy, right? Make sense? So that's something to keep in mind, that when you're doing structural design problems, sometimes you run into situations where it's certainly strong enough, but you're ended up making it larger to meet limits like this, or deflection limits, or things like that. But there's many other things going on besides just how strong the member is. There's all sorts of different checks that we have to assess, and sometimes strength, the word that we use is govern, sometimes strength doesn't govern your design. Like if we failed this limit, we might have to make the section larger because this limit is what's governing or controlling our design. Does that make sense? That can happen in our world, so just be aware of that. All right, sound good? All right, I want to really, really quickly pull up the homework that's due on Friday. So here's the homework assignment. Now, problem 1, you should be able to do with no issue because you should have been able to do that for a while. Problem 2 is I want to determine gross section yielding and net section fracture for this, so the net area is a little bit more involved. Also, I want to determine the maximum length of this angle. How long can the member be before it fails slenderness limits? And problem number 3 is similar. Well, you still have to do slenderness limits, but with problem number 3, I want to know whether or not the member is adequate. Because I've given you a dead load, I've given you a live load. The live load's already gone through live load reduction, so you don't have to worry about that. So dead load and live load, is this member adequate to resist these loads, and is it adequate under slenderness? Okay? So you should be able to do that homework start to finish. Sound good? If you haven't started it, I would definitely start it. I'm gonna have time for, on Wednesday to answer questions. With that, I just want to mention that what we're gonna do next time is get into design. And the only thing I'll say about that and then let you leave is that what we're trying to do in design is design the most economical section. And I'll talk in length about what that means, but for our purposes, that's gonna be the lightest section and the one that uses the least amount of steel. And we're gonna discuss one by one how to design according to these limit states, okay? I'm going to end it there, but we start sealed design on Wednesday, okay? Because we're actually gonna start designing a tension member, and we'll have a representative problem that we'll go through together. Sound good? That's all I got. Oh, one other thing. The only other thing worth mentioning on the homework assignment is that your shear lag factors, make sure you're using the right X bars and Y bars. Remember, connected face to the centroid. That's all I got. I will see you.